but shouldn't I get a notification that you started the recording?
Did you see that it's being recorded?
On here I do, yeah. On there, I don't know. Yeah, it's stuck. Yeah, good thing to practice. I don't know, we can wait like 1 minute. I think like, let's wait 1. I'm not a fan of starting late.
Hi everyone, we're happy to have our own Robert to give his last talk before he leaves Waterloo for science choices. He's going to talk about an improved construction of variety-evasive subspace.
All right, yeah, thanks for the introduction, Elia, and thanks everyone for coming. So today I want to tell you about this construction of these objects called variety-evasive subspace families. You're not supposed to know what these are yet. So in the talk, I'll tell you what these things are, why you might care about them, and actually I want to show you the full construction. It's a very elementary construction with a rather simple proof, modulo maybe the first week of an algebraic geometry course. If you don't know algebraic geometry, don't panic. I really want to, I tried to make this thing accessible. So this is joint work with Avivav Garg, who I think is unemployed right now, but he'll be employed as a postdoc in Toronto in about a week. So this was a really fun project working with him on this. So what are we talking about? This is a talk about pseudorandomness in computer science. So as we've all found at various points during our education and careers, like random objects tend to have amazing properties in theoretical computer science. So if you want to construct, say, Ramsey graphs or expander graphs with good parameters, if you want to construct randomness extractors, error correcting codes, find a hard Boolean function, build pseudorandom generators, any of these sort of miraculous objects that we care about finding, a random construction will give you excellent parameters for these objects. For example, a random graph will be a Ramsey graph with extremely high probability. It will be a random bipartite graph will be an expander graph with very high probability. So these are objects that are very interesting to construct. They're very easy to construct using randomness. And broadly speaking, the goal of pseudorandomness is to find efficient deterministic constructions of these objects, where you have parameters that match or come close to matching what you could achieve with a randomized construction. Okay, so these things are really easy to find with randomness, but this is kind of like a hay in a haystack problem. We want to get our hands on one of these things explicitly and deterministically. And what I want to talk about today is maybe a little bit different from a lot of these objects you've seen before. I want to talk about pseudorandom configurations in geometry, and specifically in algebraic geometry. So the theme of this talk is about constructing geometric objects that are in what's called general position. So what does it mean if some geometric objects are in general position? it means that sort of all the geometric relations between these objects are what you would expect from a random configuration. So any containments, intersections, tangencies between these objects, they should behave as if they're a random configuration. And what are these objects? These could be points, lines, planes, curves, surfaces, you name it. So let me give you some examples just to make sure we all feel what I mean by general position. So maybe the first example would be, let's take two lines in the plane. If I ask you to draw two lines in the plane, you draw a picture like this, probably. Right? You draw two lines that intersect at a point. But this is not the only way that two lines can be arranged in the plane. There are also two special configurations, one where the lines are parallel and one where you have the same line twice. Right? So here, general position would be this one intersection. Sort of if you picked two lines at random, this is the behavior you're going to get. So we're interested in finding sort of collections of geometric objects that have this general position property. Maybe a couple more examples to get a feel for this if you've never thought about it before. What about three lines in the plane? Well, if you had to draw a picture of three lines in the plane, you'd probably draw this picture. Right? You have three lines, each pair intersects, and you have three distinct points of intersection. This is what the general configuration looks like. And then there are a few special configurations. One where all three lines intersect at a common point, one where you have two intersections and two of the lines are parallel, and another configuration where you have no intersections, all the lines are parallel. And then there are even more configurations where you have lines with multiplicity. But the point here is, this configuration of three intersections, this is what's general, everything else is somehow special, right? This is what a random configuration of three lines looks like. Okay, let's think a little bit harder now. Let's think about higher dimensional examples. So what about a line in a plane in three-dimensional space? Well, general position would be the line intersects the plane in one point. Right? What would be special if the line is in the plane, or maybe the line is skewed to the plane, they don't intersect it. Right? So here, a line and a plane are in general position if they intersect in a point. One more example. What if I have two planes in three-dimensional space? If you drew this configuration, you'd see that the two planes intersect in a line in general, right? What would some of the special configurations be? Well, you could have two planes that don't intersect at all, or you could have the same plane twice. And I hope this gives you some idea of what I mean when I say these objects are in general position, right? There are no special relations. So a lot of what I want to talk about in today's talk is about vector subspaces being in general position with respect to one another. So I want to just spell out a little bit what that means if two subspaces are in general position. This really means they should intersect as little as possible. And we'll measure their intersection with their dimension. So we all know how to measure, how to compute the dimension of the intersection of two subspaces. It's the sum of the dimensions minus the dimension of their sum. And in general, what is this sum going to look like? Well, these vector spaces, they should intersect as minimally as possible. So the sum will be a direct sum up until the point where the two vector spaces fill the entire ambient space, and then you would just get the full dimensional space. So in general, the general position criterion here is that the dimension of the intersection is going to be the sum of the two dimensions minus n, the ambient dimension. But if these two spaces u and v are very small, this number might be negative, so we have to take a max with 0. It doesn't make sense for a vector space to have negative dimension. So this is what general position means for two vector spaces. They intersect in the minimum dimension possible. So just to be a little more concrete about this, say I have two planes in a 4-dimensional space, they should intersect at the origin, right? You could imagine taking two planes that in 4 dimensions, if you can imagine that they don't intersect beyond the origin. Maybe another example, if I had 3-dimensional subspaces in a 5-dimensional space, they should intersect in a line. Right? The intersections can always be bigger. This is sort of the minimal possible intersection. So these are the kinds of configurations we'll be interested in. And just, we'll capture this by saying that a space U evades V if U is in general position with respect to V. So this is what I want to do. I'm going to have some collection of these spaces V that I want to evade, and I want to find some spaces U that do this evade. Okay. So here's one of the objects we'll be interested in today. So again, we have this definition of what it means for two vector spaces to be in general position. And now I want to tell you what the sort of object we want to construct are. So say we have two collections of subspaces, script F and script H. We'll say that H is F evasive if the following property holds. For every space V in F, I can find some space U in H so that U evades V. So F is some collection of vector spaces that I'm interested in evading. H gives me some space that will evade, for every space in F, I can find a space in H that evades it. So here's a problem. Let's think about this. Let's think about all the subspaces of R to the n of half dimension. Can you construct an evasive family of subspaces for this family of vector spaces? Now, the first time you see this problem, you might think, oh, this is really easy. Because there's a really, really simple answer. You can just take the single zero subspace, right? That's going to be evasive. The origin minimally intersects every half-dimensional subspace. But that's maybe not so interesting. There's another maybe uninteresting answer, which is you could take the entire ambient space as your single vector space. And this, again, this will minimally intersect everything in script F, but this is not so interesting. So to make this problem a bit more interesting, maybe we want to add a little bit of a constraint to the evasive subspace family we construct. Say I want to construct these subspaces where they also have dimension half of ambient. So what this means is I want to, for every subspace V in script F, I want to find some other half-dimensional subspace U in script H so that their intersection is exactly the origin. Right? These two subspaces both have half the total dimension available. So this evasion just means they should intersect only at the origin. Okay. Now, if you've never thought about this before, it might not even be obvious if you can construct one of these evasive subspace families of finite size. Right? That's maybe not so obvious. If you sit down and think about it for a while, I bet you could convince yourself that a finite one of these exists. You could take all the coordinate subspaces. This will work. But in fact, a random set of only polynomial size is going to be evasive with very high probability. So this is one example where we can find this sort of random, a random construction gives us the kind of behavior we want. And it's an interesting question. Can we find deterministic explicit constructions of these objects? Okay, now this was all motivated by some fun geometry problem, but why would you care? Right? Say you come to me and you say, I really just want to do computer science. I want to design algorithms for some problems. Why would I care about constructing these objects? So there's a fun connection between these and matrix rank. So I want to tell you why you might be interested in constructing these kinds of evasive subspace families in the first place. Okay. So we have our collection of subspaces of half dimension, and we have a set script H that evades this. Okay? And script H is also a family of subspaces of half the ambient dimension. So what I'm going to do is from H, I'm going to build a collection of matrices. Okay? So for every subspace U in H, pick a matrix whose column span is that space U. Okay? And now I want to throw all of these matrices into a collection called script E. And I want to look at how this collection of matrices interacts with matrices of rank n over 2. Okay? Now I claim that for every matrix M in script M, so every matrix of half rank, there's some matrix E in script E, so that M times E is a full rank matrix. Okay, now, if you look at the dimensions M times E, this is going to be a matrix of size n over 2 by n over 2. And I claim that there's some matrix E so that M times E is full rank. It's going to remain rank n over 2. And the way you see this, well, this really follows from this evasiveness property. What does it mean for M times E to be full rank? It means that none of the columns of E should lie in the kernel of M. Right? If a column of E lies in the kernel of M, that's going to drop rank. And what does it mean so for this to be full rank, all the columns of E should lie outside of the kernel of M. Well, the kernel of M is a vector space of half dimension. And there's some matrix E whose columns will all evade that subspace. Okay, so this gives us some nice, from this family of subspaces, we can build a family of matrices that have this sort of rank preservation property. We started with a matrix that was n over 2 by n size. We reduced it to n over 2 by n over 2. We preserved the rank. And this is an object that's actually been studied before. These are what are called rank extractors. Okay, it's kind of a fun name. So these were defined back in 2014 by Forbes, Saptorici, and Spilka. They were interested in de-randomizing the polynomial identity testing problem. So what is a rank extractor? It's a collection of n by r matrices that has the following property. For every r by n matrix of rank r, there's some matrix in the extractor family so that the rank of m times e is preserved. It's still r. So one way you can think of what this is doing is M is like a collection of R linearly independent vectors sitting inside a big n-dimensional space. And what this rank extractor is doing is it's taking those R linearly independent vectors, mapping them down to an ambient space of only dimension R instead of n, but it's preserving that linear independence. So it's preserving the dimension of that space that they span. It's preserving linear independence while bringing the ambient dimension down. And that's sort of why this is maybe called a rank extractor, or sometimes they're called rank condensers. A nice slogan that I've heard of these for these is sometimes you can think of them as what's called input oblivious Gauss elimination. Right? If I gave you a set of vectors that were linearly independent and you wanted to, say I gave you a matrix. I tell you it has rank R, but you don't know which set of rows is going to be linearly independent. There's some subset of R rows. Well, you can always find a set of R linearly independent vectors in the row span by doing Gaussian elimination. Right? But this is going to be some sequence of row operations on the matrix. That sequence of operations depends on the matrix. And what a rank extractor does is it says, well, here's a few different matrices, a few different ways you could do row operations. One of them is guaranteed to work for your matrix, right? So it's a sequence of row operations that produces linearly independent vectors without seeing the matrix. And the whole game here is to understand how small you can make these sort of rank extractors. Right? You can get polynomial size rank extractors using a random family of matrices. And in fact, there are explicit constructions of small polynomial size. And why would you care about these? I mean, this is just a nice sort of linear algebraic object. But it also has connections to polynomial identity testing. It has connections to extractor theory for constructing what are called affine source extractors. Yes?
So for instance, if like M has like R independent vectors and then everything else is just garbage, like you can extract that R things?
Yes. Yes. And there are other variations on this where, this is taking R linearly independent vectors and putting them into an R-dimensional ambient space. You could ask maybe to condense the rank instead of extract. So maybe the ambient dimension only goes down to like 2 times R. Or you could ask to get a lossy version of this, where instead of getting rank R, you get rank 0.99 R. Right? There are variations on this. I can tell you more about it later if you're interested. So this is a nice object. It's one of these basic primitives in this theory of so-called linear-algebraic pseudorandomness, where we take many of the classical objects from Boolean pseudorandomness, like condensers, extractors, and so on, and we find linear-algebraic analogs of them, where subspace dimension plays a role analogous to min entropy. So that's just to say, these are interesting objects. People have studied them for, intrinsically well-motivated reasons. And if there's nothing else you take away from this part of the talk, I want you to understand that this problem of constructing subspaces that evade subspaces is completely equivalent to constructing these rank extractors. So this, cute geometry problem is actually a well-motivated problem from pseudorandomness. Okay? So subspaces evading subspaces, this is an interesting problem. Now, this is a talk about general configurations in geometry. So we talked about subspaces evading subspaces. We can talk about maybe more sort of slightly richer sets of objects or point sets that we might want to evade. So I want to tell you another example. before getting into the sort of general thing that this talk is about. So the example I want to talk about next are what are called hypersurfaces. So these are just sets that can be defined by a single polynomial equation. I'm switching from the real numbers to the complex numbers, I apologize. So these are just sets where you look at all points in n-dimensional complex space that satisfies some polynomial equation. Okay, so, and you can be a little bit more precise about it. We can say it's a degree D hypersurface if the equation is a degree D polynomial. So you've seen examples of these before in your life. For example, the unit circle. You could define this with a degree 2 polynomial, right? If we look at all points where x squared plus y squared minus 1 is 0, well, that's going to be the unit circle. And this would be a degree 2 surface. You can be a little more exotic. You can look at higher degree equations, right? So maybe you can cut out some funny looking curve in the plane using a degree 3 equation. Or you could maybe look at a set that maybe you're a little bit more motivated to care about, say, for example, singular matrices. You know, this is a hypersurface because singular matrices are exactly those whose determinant is 0. And the determinant is a polynomial function of the entries of the matrix. Okay, so what about evading hypersurfaces? So let's try to evade hypersurfaces with points. Okay? Earlier, we evaded subspaces with subspaces. Now let's evade hypersurfaces with points. So we'll say a point evades a hypersurface if the point is off of the surface. Right? That's what the general configuration would be, or that's what the minimal intersection would be. I have a surface, I have a point lying off of it. Equivalently, since hypersurfaces are defined by one equation, I can say that a point evades the surface if that equation evaluated at the point is not 0. Okay. And so now here's a problem you might consider. Let's look at all degree D hypersurfaces, and let's try to construct an evasive point set for this family of hypersurfaces, where here evasive is exactly sort of the same thing it meant earlier when we had subspaces evading subspaces. For every hypersurface in the family we care about, there should be a point in our point set that lies off of the hypersurface. And you know, this actually turns out to be equivalent to constructing what are called hitting sets for polynomials. Because saying that this point is off of the hypersurface, this is really saying for all degree D polynomials, I want to find a small set of points so that for every polynomial, there is a point where the polynomial is not 0. Now you can solve the problem as I've stated it here using the Schwartz-Zippel lemma, essentially. That gives you a deterministic construction. It's basically the best you can do. If you put further restrictions on what these polynomials are, if you put some kind of computational complexity restriction on them, then you end up with what's called the polynomial identity testing problem. And this is a very active line of research in designing explicit constructions of hitting sets in that case. So this is a second kind of evasion task we could consider. And again, if you take nothing else away from this, I want you to understand that finding points that evade hypersurfaces is exactly the same thing as constructing hitting sets for polynomials, which is a task we care about. Okay, so now I want to move along maybe and tell you a little bit more about what our work is really about, and it's about evading these more general objects called algebraic varieties. So if you haven't seen these before, an algebraic variety is just a set that I can define using polynomial equations. So earlier we saw hypersurfaces. These were one equation. Now I allow you many equations. If you've never thought about these objects before, vector subspaces are a really good example because those can be defined with linear equations. Okay, so now, the sort of object that we're interested in building are going to be evasive subspace families for varieties. We want to evade varieties using subspaces. So this is a problem originally introduced by Zheyu Guo about 5 years ago. So we have some collection script F of varieties that we care about. We want to evade these. And we're going to build a set script H. It's a collection of subspaces. And we'll say that H is F evasive if for every variety V in the family we care about, there is a subspace U in this set so that the dimension of the intersection is as small as it can possibly be. This is exactly what we saw for vector spaces. The dimension of the intersection should be really as small as possible. I'm not going to tell you what the dimension of a variety is, but it behaves like vector spaces. For example, if two vector spaces, you have two vector spaces, one is not contained in the other, so they intersect properly, the dimension of that intersection is going to drop. Same thing happens with varieties. You don't really need to know the definitions of dimension, but it behaves like vector space dimension. So this is what a variety-evasive subspace family is, this script H. And the problem is we want to construct variety-evasive subspace families for interesting collections of varieties. Right? That's the problem we're really going to be interested in. So why would you do this? Well, as we saw, this is a task that is a simultaneous generalization of constructing rank extractors and building hitting sets. If you've taken a course on algebraic geometry, you've seen something called another normalization. And these variety-evasive subspaces give you another normalizing maps. If you don't know what this is just a linear map that helps make a variety kind of look like a vector space in some sense. Not going to say more about that, but if you know what this means, you might be interested in it. And then finally, I'm just going to say, you know what, this is a nice problem. It's a nice geometric problem. It's a nice pseudorandomness problem. Let's think about it. So to tell you about the varieties that we're going to think about, I need one more definition, which is what's called the degree of a variety. And this is something you've actually seen before, you just don't know it. So we have some variety V that we're interested in, and we're going to look at this quantity called its degree. So what are we going to do? This is going to be some maximization. We're going to look at all affine subspaces U that we could pick up. So these would be lines, planes, three-dimensional subspaces, and so on. And we're going to look at the intersection of the variety V with that subspace U. And as long as that intersection is finite, I'm going to include it in my bag. And now I want to maximize over all those finite intersections. I'm maximizing the size of the intersection. So let's think about this. If the variety was actually a vector subspace, then this number is going to be 1 at most. So it's going to be a degree 1 variety. If you have a curve in the plane, say you think about the graph of a degree 2 polynomial equation, well, that would give you a degree 2 variety, right? Think about a parabola and you try to intersect it with a line. You can get at most 2 intersections between a parabola and a line. Right? A circle and a line, you can get at most 2 intersections. So a circle has degree 2, and so on. This is just some measure of some sort of geometric complexity of the variety, sort of how much it curves around in space. Higher degree means they curve around more and they hit these affine subspaces more. Okay, right. Oh, examples. Yeah, so vector subspaces have degree 1. The circle has degree 2. What about the determinant hypersurface? So singular matrices. Well, this is a hypersurface. It's cut out by a degree n polynomial equation. And for hypersurfaces, the degree of the variety is exactly the degree of this equation. So the set of singular matrices, this is a variety of degree n. This is something of higher degree that maybe you haven't thought of before. Okay, so now onto the variety-evasive subspaces. So here's the family of varieties we're going to be interested in. These are varieties in n-dimensional space of degree at most d. And we want to construct subspace families that evade all varieties in this script. Okay? Of course, if I didn't bound the degree, I'd just be looking at all varieties, and this is kind of an impossible task. So we need some way to control these. Now, random sets of sufficiently large size will give you evasive subspace families. And this was the problem that Zayu looked at in his paper, was giving explicit constructions of variety-evasive subspace families. So Zayu was the first to ask this question, and he found a construction of F-evasive subspaces. And if you want to construct a family of evasive k-dimensional subspaces, he gives a construction with this size. It's polynomial in D, the degree of the variety, And then n raised to, well, there's a minimum of 3 things. There's k, which is the dimension of the subspaces that do the evading. There's n minus k. And then there's d, the degree of the variety. And so maybe for concreteness, you can think of k as being like n over 2, right? This exponent gets smaller as k goes closer to 0 or closer to n. And we saw earlier this example where you can evade sort of any linear subspaces using just the origin or just the entire space, right? So this problem gets more challenging when you're using subspaces of about half the dimension. So think of that. So this exponent would be about, n over 2 times d. Right? D is generally going to be much larger than n. So for example, I'll say when d is constant, Zayu gives a construction of polynomial size. And he also complements this with a lower bound on the size of any such variety-evasive subspace family. And the lower bound is just n minus k plus d, choose d. Okay, and how you should think about this is, well, when d is a little bit larger than n, like a little bit, meaning like it's n to the 1 plus epsilon, this lower bound is about d to the n minus k. Okay, so there's an upper bound, which is, let's think about this maybe as n to the power n minus k times d. And the lower bound is d to the n minus k. So there's a d in the exponent up here. There's a d just in the base down here. That's kind of a big difference. And so the question we were interested in is, how much can we close this gap? Can we find, explicit constructions of smaller size? Can we improve on this? It turns out in some parameter regimes, this lower bound is matched by a non-explicit construction. So improving the lower bound is maybe not such an easy thing to do. So now I can tell you about our results. So we give an explicit construction of these variety-evasive subspace families of smaller size. So if we want to evade n varieties in n dimensions of degree d using k dimensional subspaces, we give a construction of size n times d plus 1 raised to the power n minus k. Okay, so for comparison, the previous construction from Zayu had this size. So the main point here is that this d that was in the exponent now has moved into the base. And as I told you, there's also this lower bound of d to the power n minus k when d is a little bit larger than n. And in this parameter regime where d is a little bit larger than n, our construction is really of size like d to the order n minus k. Right? So up to this constant in the exponent, in this regime, we're more or less getting the right construction. There's a polynomial factor in size that you could try to optimize. But I think this is kind of nice that, at least in this regime, you're getting nearly the optimal thing. And I should mention that in general, this degree can be even exponentially large. So asking for polynomially large degree is not such a restrictive ask. So this is the first result. We have a second result, which is a little bit stronger than this. So in this definition of evasive subspace families, the definition was that for every variety, there exists at least one subspace that evades it. You could ask for some stronger guarantee, maybe for every variety, most of the subspaces evade it. So we also have a result in this direction. So our second result, which is really just a mild extension of the first in terms of the techniques. So for every parameter epsilon greater than 0, we give a different explicit construction of subspaces that on the one hand are a little bit stronger than just being evasive. So for every variety in the family we care about, every degree d variety, at least a 1 minus epsilon fraction of the subspaces will evade that variety. So for each variety, most of our subspaces evade it. Okay, so this is a stronger guarantee on the kind of evasion we get. Then we have to pay a price in terms of the size of the family. So now we lose some polynomial factor in terms of the size of the family I showed you on the previous slide. And we also incur some polynomial in 1 over epsilon dependence here. And so if you pay an extra, basically polynomial in 1 over epsilon, you can get this stronger guarantee. And I should say we weren't the first ones to do this. Zayu in his work also constructs evasive subspace families with this stronger guarantee. Maybe I'll just pause here. Are there any questions about the result or why you might care about it? Because otherwise I can just tell you how to construct this and prove it. Yes?
Is it easy to find the U that evades V in H?
Oh, no. Yeah, no. It's if you gave me V, I don't know how I would produce U deterministically.
And in general, do you know if there's any arguments for these kinds of questions? Like if you have a family of subspaces and you want to find.
Yeah, that's a good question. I don't know. But let's chat about it more.
Okay.
Yeah. Any other questions? Okay, so in the rest of the talk, I just want to show you the construction of this evasive subspace family. So how we get this improved bound in the at least one subspace must evade case. My hope is to convince you of the correctness of this in the remaining part of the talk. So I hope I can do that. Okay, so I need one slide about algebraic geometry. I apologize, I don't want this to be the first week of an algebraic geometry course. So I'm just going to say as little as I need to. And I hope that if you've never seen this before, you're willing to believe me and follow along. But I hope that it can still illustrate what's going on. Okay, so I need a definition. So a variety is what's called irreducible if you can't write it as a union of two smaller varieties. Okay. So think about vector spaces. Vector spaces are varieties. Can you write a plane as a union of two smaller vector spaces? Well, what's a smaller vector space than a plane? It has to be a line. And I can't write a plane as the union of two lines. So planes are irreducible. Vector spaces are irreducible. And there's a nice fact. So why is irreducibility an interesting thing to look at? Because we can characterize evasion extremely nicely for irreducible varieties. So what does it mean for a hyperplane to evade an irreducible variety? Well, they should intersect as minimally as possible, which, when you work out the definitions, means that the dimension of the intersection should drop by 1. If you think about a vector space, what does it mean for a hyperplane to evade it? That hyperplane should introduce one new linear constraint. So your dimension should drop by 1. Same thing with varieties. And you can actually characterize this in an extremely simple way. There should be a point on the variety, not on the hyperplane. Same thing with vector spaces. If I have a vector space and a hyperplane, there's a point in the vector space, not on the hyperplane. That means I introduced a new linear constraint. I'm missing some of that vector space. Okay. So the point here is for irreducible varieties, evasion really just means there's a point on the variety, not on the hyperplane. And then I need a second fact. So why did I tell you about degree in the first place? Well, one reason is that you can always write a variety in a unique way as a union of irreducible varieties. So this is sort of akin to how numbers can always be factored into primes. Varieties can always be decomposed into irreducible parts. And how many parts are there? There's at most degree many parts. Okay. So these are this is all the geometry we need. If you're willing to believe me on what's on this slide, we can construct the evasive subspace family. Maybe I'll just linger on this for a few seconds. Does anyone have any questions? Okay, so let's do a warm-up. So the goal for this slide is I want to construct an evasive family of hyperplanes. So I want to find a family of hyperplanes that evades every degree D variety. So I claim that we can find an explicit construction of these hyperplanes where I have n times D plus 1 hyperplanes in the evasive subspace family. Okay, so how are we going to do this? So let's pick a variety and let's try to evade it. We have this degree D variety. It breaks up into irreducible pieces. There's at most D of them. So what I'm going to do is on each of the irreducible parts, pick a point. Any point, it doesn't matter which one. From what I showed you on the previous slide, to evade this variety, it's enough for me to find a hyperplane U that does not contain any of these points. On each irreducible part, it's missing some point. Okay? That's all I need to do. I need to find a hyperplane that doesn't contain these points. So here's what we're going to do. We're going to use the polynomial method to build these hyperplanes. So let's look at this polynomial. It's going to be useful to find a hyperplane that avoids the ith point. Okay, so we have n variables here, y1 through yn, and it's this polynomial, y1 times the first coordinate of pi plus y2 times the second coordinate, and so on. And now, if you think about it, say I evaluate this polynomial at some point a, and I get a non-zero evaluation, then that means that this point P was not in the hyperplane defined by A. All the points in this hyperplane are things where A1 times the first coordinate plus A2 times the second coordinate and so on, that should sum to 0. And if Fi at A is not 0, well, what's Fi at A? It's exactly A1 times the first coordinate of Pi plus A2 times the second coordinate of Pi and so on. So saying that this is not 0 really means that this point is not on this hyperplane. And so I can take the product of all these polynomials. And if the product is not 0, that means that each point Pi is not on this hyperplane. So if this product of polynomials, if I can find a point where this evaluation is non-zero, then I get this hyperplane that evades my variety. And in particular, I didn't really care what these points were. I just know they have to exist. Okay, well, this product of polynomials, what do we know about it? Well, each of the factors is a degree 1 polynomial in n variables. And how many factors are there in total? Well, there's at most d factors, because we have one factor for each of these irreducible parts of the variety. And we have at most d of them. So we have a degree d polynomial in n variables, and I need to find a point where it's not 0. This is the problem of constructing a hitting set for these guys. And short Zippel tells you you can find one of these non-zero evaluations in any set of size d plus 1 to the power n. So this gives us an evasive subspace family, not of the promised size, not this nd plus 1, but d plus 1 to the power n. Okay, so much worse than I promised you, but we're actually almost there. We just need to pick a slightly different set of polynomials. So we're going to run the same argument, but we're going to change this first polynomial here. Okay, so instead of picking these coefficients, y1, y2, and so on completely independently, let's pick them in a different way. Let's look at this polynomial. Now it's a univariate polynomial where I have a single variable y, and I look at y times the first coordinate of pi, plus y squared times the second coordinate, plus y cubed times the third coordinate, and so on. And again, we have the same kind of logic that if f evaluated at some point a is non-zero, then I know that the ith point pi does not lie on this hyperplane. Okay. Now, why should one of these points, why should such an a exist in the first place? Well, what would it mean for f of a to be 0? That means you have some univariate polynomial, its coefficients are the coordinates of pi. It would be a 0 of that polynomial, but this is a degree n polynomial. It has at most n roots. I guess one thing that maybe I glossed over is the point pi here should not be the origin. These should not all be 0, but you can guarantee this. Okay, and so now, same kind of logic. We take the product of all these polynomials, and if we find a point where the product is non-zero, then this means that this hyperplane evades the variety V because each of these points pi was off of the hyperplane. And now the bonus is that if you look at this polynomial, this is a polynomial of degree n times d. Each factor is degree n. There are at most d factors, so degree n times d. But now it's in one variable. So how do you find a point that's not a root of a univariate polynomial of degree n times d? You pick n times d plus 1 points. That's it. So this gives you a construction of hyperplanes that evade these low degree varieties. And a claim that we're almost done. We can just iterate this construction and get the evasive subspace family we wanted. So now here's the full construction. So let's take a set of nd plus 1 many points, S1, pick a disjoint set of, again, nd plus 1 many points, S2, and so on. I have all these different sets of n times d plus 1 points. They're all disjoint. And for each a, I'm going to look at this hyperplane that we were talking about before, where the coefficients are a squared, a cubed, and so on. So the lemma I showed you on the previous slide is that if you look at all the hyperplanes where you take this parameter from the first set S1, this is an F-evasive family of hyperplanes. Okay, this is what we wanted. And it turns out the full construction is you just take intersections of these hyperplanes. And this gives you your evasive subspace family. So if you want to construct a family of k-dimensional subspaces that evade these varieties, you pick some A1 from S1, A2 from S2, and so on. You build these hyperplanes, you take their intersection. That's your evasive subspace family. So, it's very nice, it's explicit. You can write down an efficient deterministic algorithm that will print all these subspaces. Why is this an evasive subspace family? Well, it's essentially, a proof by iteration or by induction. So if you have some variety you want to evade, we know there's a point A1 in S1 so that this hyperplane evades the variety. So what does evasion mean? It means that the dimension drops. Now, if we want to continue by induction, we also want to know that this intersection, this U intersect V, still has degree at most D. Bezout's theorem, one more fact I need from algebraic geometry, says that the degree is not going to go up. And so, using this lemma we saw on the previous slides, we can find another hyperplane defined by the parameter A2 so that this plane evades this intersection of UA1 intersect V. But rephrasing this is exactly the same thing as saying the intersection of UA2 and UA1 evades V. So now I found not a hyperplane that evades V, but I found a codimension 2 subspace that evades V. And you can continue by induction. Every time the codimension of this subspace increases, you're adding another factor of n times d plus 1 to the size of the subspace family. So that's it. That's the whole construction. So let me end with just some open questions from this work and things that I think are maybe interesting to think about. So one question is, can you get an explicit construction of these variety-evasive subspace families of near optimal size? This is maybe a bit of an obvious open question, but there's some polynomial gap in some regimes between our upper bound and the lower bound. Can you close that? Can you find better constructions for varieties that have low complexity descriptions? So this was looking at all varieties of some degree, but you could, for example, ask that you only care about evading varieties that can be described very efficiently, say with a small algebraic circuit. That seems like it could be an interesting question to study. There's also some sort of moderate degree regime where we really don't seem to have the right answer yet. So for example, for varieties of degree square root n, if you want to construct subspaces of half dimension that evade them, the best explicit construction has size exponential in n, but the lower bound is only n to the root n. So you have this n versus root n in the exponent. It would be interesting to find a construction that closes that gap or improves on that. And then finally, the last question is, there are some applications of these in pseudorandomness, but most of the applications really do come from either rank extractors or hitting sets. There is this application I mentioned to another normalization, but that's almost definitional. It's not truly an application. So I think finding more applications of these objects in computer science would be nice. Maybe you'll find some way to use these in your research. If you do, let me know. I'd love to hear about it. So that's it, everyone. Thanks so much for your time. Questions? Okay. Great, thanks.